Constraint programming is the declarative programming paradigm. Let's see what it means. So if you remember, constraint programming is a complete method. What it means is that granted you give it enough time to solve the problem, it will either find a solution or it will prove that no solution exists. So that's a little bit different from heuristics, because heuristics most of the time don't offer that kind of guarantee. And to find a solution, we will explore a search tree. So constraint programming is really a technique that tries to focus on feasibility. And the focus on feasibility will be achieved thanks to the constraints. The constraint will really prune infeasible space of the search space by removing values from the domains that do not belong to any solution. But constraint programming is also focusing on reusability. It means that once you have implemented the constraint in your solver, you can reuse that constraint and that implementation in many different types of contexts. So you can really see constraint programming as a Lego tool, for instance, or a Swiss Army knife like this one. So all the different types of tools that you have on this Swiss Army knives represent one constraint, or each Lego here bricks represent also one constraint, and you can reuse them to assemble and reassemble them to model your specific problem. So one famous sentence that was stated by Eugene Freuder is constraint programming represents one of the closest approach of computer science, one of the closest approach that computer science has ever made to the holy grail of programming. The user states the problem and the computer solves it. So what is important to realize is what we mean by stating the problem. Surely, currently, we don't state meaning the problem mentally, right? It's not exactly what we mean. What we mean by stating the problem, we mean describing in a high-level language, describing your problem in terms of constraints. That's, for instance, a kind of pseudocode that you could imagine for the n queens. But in the future, who knows what we can achieve? Maybe we will be able to state problems in a much more declarative way, as we are doing now in a programming language. So in declarative programming, the programmer expresses the logic of the computation, but does not really describe the control flow. So declarative programming means that you just express the properties that need to be satisfied by the solver that is in charge of finding a solution to the problem. So you really describe the properties, so the constraints that needs to be satisfied. Usually, we also say that constraint programming is composed of two very important components. One is the model and one is the search. The model uses the API of the constraint programming solver, and you assemble all the variables and you link them with constraints that are available in the API. And the search is the algorithmic part. It's in charge of finding a solution that satisfies all the constraints, and it's usually performed by exploring a search tree. So the model is composed of the variables and the domains, plus the constraint that link all the variables. You can have various types of constraints. For the n queens, we have just one type of constraints. We have the different constraint, but in programming solver, constraint programming solver, you might also have arithmetic constraints, logical constraints with Boolean relations. You can also have combinatorial constraints, such that this kind of constraint should represent, this variable should represent a Hamiltonian circuit, for instance, if you want to solve a problem such as the traveling salesman problem. Let's see one example here. So we have a vessel, and this vessel should visit each dot here, and it should also minimize the total traveling distance. Okay, so one possible way to model that problem is to introduce one variable xi that will represent the next city that you will visit just after visiting the city I in the tour. Okay, that's really how we would model the traveling salesman problem in CP. And the domain of each variable xi is composed of all the city except the city I itself, because we want to prevent self loops. So that's the way we would model with what we call a successor model, the TSP. And the constraints, as I said, there are various types of constraints. You can have some constraints, for instance, to collect the total traveling distance traveled by the traveling salesman. You can have logical constraints. You can have global constraints to impose that a set of variables should take all different values. So there are many different Lego bricks that are available in solvers. And the application domains are also very broad for constraint programming. So you might use constraint programming to solve a scheduling problem that's represented on the left. For instance, that's the job shop problem. You might also want to use CP to solve a vehicle routing problem or even a rostering problem, for instance, to schedule the exams in your universities. So if you want to solve, for instance, the job shop problem, that's a problem in which you have a sequence of tasks. So that's part of a scheduling problem. So you have a sequence of tasks that needs to be scheduled one after the other. And each task has, each activity has a color that represents the resource on which it should execute. And obviously, because the capacity of the machine is 1 in this case, you cannot have two activities of the same color that overlaps each other. Well, in constraint programming, it's very easy to express this problem. We have a Lego brick that's called the disjunctive constraints just to model this kind of problem. And so with the disjunctive constraint, if you project all the activities on the resource, the corresponding resource, you see that they do not overlap each other. So we have a specific constraint in CP just to enforce this type of constraint. But we have different types of constraints for many different types of problems in CP. That's just one example. So the way we would model problems with CP is very different from the way we would model problems with mixed integer programming. Because in mixed integer linear programming, you are restricted to use linear types of constraints most of the time. And so expressing the fact that you want to visit every city only once and that should form an Hamiltonian circuit, it's not really easy in terms of linear constraints. You should use the subtool elimination techniques and you need to state an exponential number of constraints for that. In CP, if you want to model in a declarative way this kind of problem, you can use just the circuit constraint and then you can use an arithmetic sum constraint to collect all the traveling distance performed by the salesman by visiting one city after the other. So that's very high level, and that's the way we would model this kind of problem in a declarative way in CP. And you can also index arrays with variables. That's called the element constraint, and we will come back to that later. So it's a very rich modeling language that we have in CP to model.